Have you ever stood in a place of profound silence, far from the ceaseless, incandescent hum of the city, and looked up into the unfiltered, absolute darkness of the night sky? Have you ever felt that dizzying, vertiginous sensation, a feeling of falling upwards into an abyss of impossible silent depth, a quiet terror mixed with an exhilarating sense of awe? It is a feeling that is at once both deeply humbling and quietly terrifying, a visceral, primal reminder of our own infinitesimal smallness in the face of a universe that is vast beyond all human scales of comprehension, a universe that is utterly indifferent to our existence. We are creatures of the surface, bound by the invisible, unbreakable tether of gravity to a tiny, fragile world of rock and water, a pale blue dot adrift in an immense and lonely cosmic ocean. And yet, for as long as we have been human, for as long as we have possessed the cognitive spark of wonder, we have been irresistibly drawn to that dark, glittering expanse above. We have yearned to understand it, to map its uncharted shores, to measure its unfathomable depths. To do so, to bring this cosmic wilderness into the realm of human knowledge, we have had to invent a language, a system of measurement capable of spanning the silent, lonely gulfs that separate the stars. For most of us, that language is the language of light. We speak of light years, a unit that is both scientifically precise and deeply, wonderfully poetic. It is the distance that a single photon of light, the ultimate cosmic messenger traveling at the absolute speed limit of the universe, covers in the course of a single, familiar, terrestrial year. It is a concept that beautifully and inextricably weds the vastness of space with the deep, flowing river of time, distance with history. It allows us to look at a star 1,000 light years away and understand, on a fundamental, intuitive level, that we are not seeing it as it is now, but as it was 1,000 years ago, when our own world was a vastly different place, a world of castles and crusades. We understand that its light has been on a millennial journey, a solitary pilgrimage across the void, just to end its long existence in the pupil of our eye. The light year is the language of wonder, the currency of science fiction, the unit that has carried us to the farthest reaches of our imaginative cosmos, from the bridge of the Starship Enterprise to a galaxy far, far away, far away. But what if I told you that this language, the one we all know and intuitively understand, the one that has become synonymous with the scale of the cosmos in our popular culture, is not the language spoken by the very people who professionally navigate this cosmic ocean? What if I told you that in the hallowed, silent halls of observatories, in the dense, equation-filled pages of astrophysical journals, the light year is a foreign tongue, a piece of poetic whimsy with little practical application? There is another language, a secret language, a strange and beautiful measurement that astronomers use, a unit that seems, on its face, to make no sense at all. It is a unit born not from the speed of light, not from any fundamental constant of nature, but from the simple, elegant, and ancient geometry of a triangle. It is called the parsec. The word itself has a certain archaic, science fiction ring to it, as if it were a relic from a forgotten pulp novel of the 1950s. And yet, it is the absolute bedrock of modern astronomy. It is the fundamental unit upon which the entire towering edifice of the cosmic distance ladder is built. Without the parsec, our knowledge of the universe, our understandings of its size, its age, its very structure, would be a house of cards, beautiful but fragile, liable to collapse at the slightest breath of uncertainty. So why is this? Why do the professionals, the cosmic cartographers, use this strange, seemingly arbitrary unit? Why is the parsec so fundamentally important, and the light year, for all its poetic beauty and intuitive appeal, relegated to the realm of popular science and public outreach? This is the central mystery we will investigate. This is the story of the parsec. It is a detective story, a 2,000-year-long mystery, a tale of a ghost that haunted the minds of the greatest astronomers in history. A phantom they chased through centuries of frustration and failure. It is a story of human ingenuity, of relentless, single-minded obsession, and of a final, triumphant breakthrough that forever changed our place in the universe. If you have ever felt that the universe is a place of deep mystery and hidden truths, then you are in the right place. Join us on this journey into the heart of the parsec paradox. And if you believe, as we do, that these profound questions are worth exploring, consider liking this video and subscribing to Cosmodepth. Your support is the fuel that allows us to continue our exploration of the cosmos. Now, let us dim the lights, cast our gaze back in time, and begin our journey into the strange, wonderful, and utterly essential world of the parsec. We live in a universe of two languages, a cosmos bisected by a linguistic divide. There is the public language of wonder, and there is the private language of the professional. The light year is the public language. It is the language of Carl Sagan's Cosmos, a series that invited a generation to walk the shores of the cosmic ocean. It is the language of Star Trek and Star Wars, of every popular science documentary you have ever seen. It is a brilliant and indispensable tool for communication, a way of making the incomprehensible scale of the universe feel, if not manageable, then at least approachable. It connects the abstract alien concept of interstellar distance to the familiar human concept of time. It allows us to feel the deep history of the cosmos, to understand that looking out into space is also, and always, looking back into the past. It transforms a simple point of light into a time capsule, a messenger from a bygone era. But the parsec is the private language. It is the secret handshake of the astronomer, the insider's jargon. It is a unit that is as practical and as unpoetic as a surveyor's theodolite or a mechanic's wrench. It is a tool for doing a job. And that job is the precise, quantitative, and unforgivingly difficult business of measuring the universe. To the outsider, it seems deliberately obscure, a piece of arcane terminology designed to keep the uninitiated at bay, a barrier to entry into the exclusive club of professional astronomers. But to the insider, to the person who spends their nights in the cold, silent dome of an observatory, it is the most natural, the most logical, the most elegant unit imaginable. It is a unit that is so perfectly and exquisitely tailored to its task that to use anything else would be like trying to perform surgery with a butter knife. The existence of these two languages, this great divide between the parsec and the light year, is the central clue in our mystery. It tells us that there is something unique, something special, something absolutely fundamental about the parsec that makes it indispensable to the working astronomer. To understand what that is, we must embark on a historical journey. we must go back to the very beginning of astronomical thought, to a time before distance was a concept that applied to the stars, a time when the universe was a much smaller, much more intimate, and much more human-centered place. Let us transport ourselves back in time, across the chasm of centuries, to the sun-drenched shores of the ancient Greek world. Imagine a world without the pervasive glow of electric light, a world where the setting of the sun revealed a celestial spectacle of breathtaking brilliance, a familiar and constant companion to human life. For the philosophers and astronomers of this age, for Plato, for Aristotle, and for the countless generations that followed in their intellectual footsteps, the universe was not a vast, cold, and empty void, but a finite, ordered, and perfect creation, a cosmos in the truest sense of the word, meaning order. At the absolute center of this universe, immovable and supreme, was the Earth, and surrounding the Earth, like the layers of a divine onion, were a series of nested crystalline spheres, each one transparent and perfect, each one rotating with the silent, flawless precision of a divine mechanism. The moon was attached to the first and closest sphere. The sun, the giver of life, was attached to another, more distant one. And each of the planets, the celestial wanderers, was fixed to its own sphere. On the final, outermost sphere, the boundary of the known universe, were the stars. They were not distant suns, burning with their own unimaginable fire, but tiny, fiery points of light, all fixed at the same, ultimate distance, all part of the same grand celestial architecture. This was the firmament, a concept inherited and refined from even more ancient Babylonian and Egyptian cosmology. It was a model of the universe that was not only scientifically plausible, given the available evidence, but also deeply philosophically and emotionally satisfying. It gave humanity a central, privileged place in the grand scheme of things. It provided a sense of order, of stability, of permanence, in a world that was often chaotic and unpredictable. The stars rose and set with the precision of a celestial clock, a divine machine that governed the cycles of the seasons, guided sailors on the featureless sea, and provided a timeless, unchanging backdrop for the myths and legends that gave meaning and structure to human life. In this universe, the question, how far away is that star, was a nonsensical one, a category error. It was like asking how far away a particular brushstroke is on the ceiling of the Sistine Chapel. The answer is that it is as far away as the ceiling itself. The stars were all part of the same object, the same celestial sphere. There was no depth to the heavens, no concept of a third dimension stretching out into the lonely, silent infinite. But this perfect clockwork universe had a problem, a small but persistent anomaly that nagged at the minds of the most careful observers. There were a handful of objects in the sky that refused to play by the rules. Amidst the predictable nightly procession of the stars, there were 7 celestial bodies that moved with a strange and unsettling independence. These were the sun, the moon, and the 5 bright points of light that the Greeks named planets, the wanderers: Mercury, Venus, Mars, Jupiter, and Saturn. To the naked eye, they looked like particularly bright stars, but their behavior was anything but star-like. They drifted slowly but inexorably across the sky, night after night, against the fixed backdrop of the constellations, following the same general path as the sun, the ecliptic. Their motion, however, was complex and deeply puzzling. they would speed up, slow down, and sometimes, in a display of cosmic defiance that seemed to challenge the very notion of an ordered universe, they would halt their eastward progress, reverse course, and move backward to the west for a period of weeks or months, before once again resuming their forward journey. This retrograde motion was a profound and fundamental challenge to the simple, elegant model of the celestial spheres. How could an object be attached to a smoothly rotating sphere, yet move with such an independent, almost willful abandon? To solve this puzzle, the Greek astronomers, who were mathematicians of unparalleled genius, devised a system of breathtaking complexity and ingenuity. The culmination of this monumental effort was the work of Claudius Ptolemy, a Greek-Roman astronomer who lived and worked in the great city of Alexandria in the 2nd century AD. The Ptolemaic system, laid out in his masterwork, the Almagest, was a true masterpiece of geocentric cosmology. In it, each planet was attached not directly to its main sphere, the deferent, but to a smaller, rotating circle called an epicycle. This epicycle, in turn, was attached to the deferent, which revolved around the Earth. It was a universe of wheels within wheels. As the deferent rotated, it carried the epicycle with it, and as the epicycle rotated, it carried the planet. The combined motion of these two circles could, with the right choice of sizes and speeds, reproduce the observed motion of the planet, including its retrograde loops, with astonishing accuracy. For even greater precision, Ptolemy introduced further refinements, such as the equant, a point offset from the Earth, from which the motion of the deferent appeared uniform. It was a system of immense mathematical power, a complex and finely tuned piece of celestial machinery that was able to predict the positions of the planets for centuries to come. It was a triumph of mathematical modeling, a testament to the power of human reason to find order in apparent chaos. And it was completely, utterly, and profoundly wrong. But it was so successful and so deeply entrenched in the philosophical and religious thought of the time that it would dominate Western astronomy for the next 1,400 years, a monumental and enduring testament to the power of a beautiful and beautifully wrong idea. Even in the ancient world, however, in the sunlit intellectual landscape of classical Greece, there were whispers of a different reality, a dissenting voice that spoke of a cosmos of a radically different design. In the 3rd century BC, a century before the great Hipparcos, and 4 centuries before Ptolemy would cast his geocentric model in what seemed like immutable stone, a Greek astronomer and mathematician from the island of Samos named Aristarchus proposed an idea that was so audacious, so far ahead of its time, that it was almost entirely ignored. Dismissed as the fanciful speculation of a mind untethered from common sense, Aristarchus suggested that the Sun, not the Earth, was the true center of the known universe. He proposed that the Earth was not the fixed and stable foundation of all things, but was just another wanderer, another planet, orbiting the central fire of the Sun in a great circular path, and spinning on its own axis once a day to create the illusion of the rising and setting sun. This was the heliocentric model, and it was a stunning, breathtaking leap of the imagination. It was a model that was far simpler, far more elegant, and far more mathematically beautiful than the convoluted system of epicycles that would follow. It explained the puzzling retrograde motion of the planets in a natural and straightforward way, as a simple illusion of perspective caused by the faster-moving Earth overtaking a slower-moving outer planet like Mars or Jupiter. But it was too much, too soon. It seemed to fly in the face of all human experience. We do not feel the Earth moving beneath our feet. We see the sun and the stars revolving around us in a daily procession. The idea of a moving Earth seemed not just wrong, but absurd, and it raised a new and seemingly fatal objection, an observational test that the heliocentric model had to pass, and which it spectacularly failed. If the Earth was indeed orbiting the Sun, then our vantage point on the stars was constantly changing. Over the course of a year, we would be viewing the stars from opposite sides of our orbit, a baseline of immense, unprecedented size. This should cause the nearby stars to appear to shift back and forth against the fixed backdrop of more distant background stars. This is the phenomenon of parallax, a simple effect of perspective. You can demonstrate it for yourself in this very moment. Hold your thumb up at arm's length, close your left eye and line your thumb up with a distant object. Now, switch eyes, closing your right and opening your left. Your thumb will appear to have jumped to the side. This apparent shift is parallax. The ancient Greeks, with their mastery of geometry, understood this principle perfectly well. They knew that if the Earth was moving, the stars should show a parallax shift. They looked for it. They used the most precise instruments they had, simple sighting tubes and cross staffs. But they found nothing. The stars remained stubbornly, maddeningly, perfectly fixed. For the astronomers of the ancient world, this was the definitive observational proof that the Earth was stationary. The absence of any observable parallax could mean only one of two things. Either the Earth did not move, as common sense and philosophical tradition dictated, or the stars were so mind-bogglingly, incomprehensibly far away that their parallax shift was too small to be detected by the instruments of the day. For the ancient mind, with its cozy, human-scaled universe, the first option was by far the more plausible, the more rational, the more comforting choice. The idea of a universe of such vast, empty scale was not just scientifically unlikely, it was philosophically and emotionally terrifying. And so, the heliocentric model was dismissed as a clever but flawed speculation. The question of the true distance to the stars was put to rest, and the ghost of parallax, the silent, unseen shift of the stars, would have to wait for nearly 2 millennia for its moment of vindication. A long, patient sleep before its dramatic reawakening. For 14 centuries, the Ptolemaic universe, with its stationary Earth, its celestial spheres, and its intricate dance of epicycles, remained the accepted truth, a monumental intellectual edifice that seemed as solid and as eternal as the heavens themselves. But the Renaissance, a great and turbulent flowering of art, culture, and science that swept across Europe, brought with it a new spirit of inquiry, a restless and rebellious willingness to question ancient authorities and to look at the world with fresh, unaccommodated eyes. It was in this environment of intellectual ferment that a Polish cleric and astronomer named Nicholas Copernicus, working in the quiet solitude of his study in Frombork, would once again set the Earth in motion, and in doing so would trigger a revolution that would forever change humanity's place in the cosmos. Copernicus was a cautious and deeply religious man, acutely aware of the revolutionary and potentially heretical implications of his work. He spent decades refining his heliocentric model, a universe in which the Earth and the other planets revolved around a central, stationary sun. He knew that his ideas would be met with fierce opposition, not just from the powerful institution of the Church, but from the deeply conservative academic establishment, which had built its entire worldview on the foundations of Aristotle and Ptolemy. It was only on his deathbed, in 1543, that he finally allowed his masterwork, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, to be published. The Copernican Revolution had begun, but it was a quiet revolution at first. The mathematics were dense and complex, and the implications were deeply unsettling to the established order. For several decades, the Copernican model was treated as little more than a mathematical curiosity, a clever computational device for predicting the positions of the planets, but not a true physical description of reality. It was not until the early 17th century, with the work of the flamboyant, brilliant, and combative Italian astronomer Galileo Galilei, that the revolution would explode into the public consciousness and become a matter of intense and dangerous debate. Galileo was one of the first to turn a new and marvelous invention, the telescope, to the heavens. And what he saw there with his own eyes would tear the old universe apart, providing a flood of empirical evidence for the Copernican system. He saw that the moon was not a perfect, ethereal orb of celestial matter, but a rugged, cratered world with mountains and valleys, much like the Earth. He saw that the planet Jupiter had 4 moons of its own, a miniature solar system that proved unequivocally that not everything in the cosmos orbited the Earth. He saw that the planet Venus went through a full set of phases, just like our moon, a discovery that was impossible to explain in the Earth-centered Ptolemaic system, but was a natural and necessary consequence of a sun-centered model in which Venus's orbit lay inside that of the Earth. The evidence was clear, direct, and irrefutable. The old world of Ptolemy was dying, and a new, vaster, and more challenging universe was being born. But this new, sun-centered universe brought the old, unresolved problem of parallax back to the forefront of astronomical thought with a new and desperate urgency. If Galileo was right, if the Earth was indeed hurtling through space on a vast orbit around the Sun, then the stars simply had to show a parallax shift. The logic was ironclad. The absence of this shift was the last great refuge of the defenders of the old system, the single most powerful scientific argument against the Copernican model. The astronomers of the 17th century found themselves in a deeply uncomfortable and paradoxical position. They had a theory that was beautiful, elegant, and supported by a wealth of new telescopic evidence. But to fully accept it, they had to embrace an implication that was almost too staggering to contemplate. The fact that they could not, for all their efforts, detect any stellar parallax meant that the stars were not just a little further away than Saturn, the most distant known planet at the time. They had to be thousands, perhaps millions, of times further. The universe had to be a place of such profound, empty distances that the Earth's entire orbit, a journey of nearly 200 million miles, was reduced to an insignificant, infinitesimal point. This was a psychological and philosophical shock of the highest order. The cozy, enclosed, human-scaled universe of the ancients was gone forever. replaced by a cosmos of terrifying, near-infinite scale. Humanity was no longer at the center of a divine and purposeful creation, but was adrift on a tiny speck of dust in a vast, dark, and seemingly indifferent ocean. The quest to measure stellar parallax was no longer just a matter of settling a scientific debate. It was a quest to find our place in this new, vast, and intimidating universe. It was a race to confirm the true scale of the cosmos, to finally and definitively prove that the Earth was a planet, the Sun was a star, and the stars were other suns, scattered across an ocean of unimaginable depth. The great silence of the stars, the absence of any discernible shift, was a challenge thrown down to the astronomers of the world. And it was a challenge that would consume the lives and careers of the greatest scientific minds for the next 200 years. And so began one of the great, unsung epics in the history of science. The 200-year race to measure the parallax of a star. It is a story often overshadowed by the more dramatic revolutions of Copernicus, Galileo, and Newton, but it is no less important. It was a slow, grinding, and often frustrating battle, fought not with grand theories, but with brass instruments, cold nights, and an almost fanatical devotion to precision. It was a multi-generational relay race, with each generation of astronomers building on the hard-won knowledge of their predecessors, refining their instruments and pushing the limits of what was technologically possible, only to find that the universe was always one step ahead, its true scale always just beyond their grasp. The challenge they faced was almost absurdly difficult, a task of measurement so delicate that it bordered on the impossible. The angle they were trying to measure, the annual parallax of even the nearest stars, was known to be incredibly small, a tiny fraction of a single arcsecond. An arcsecond is 1/36th of a degree. To put that into perspective, it is the apparent width of a human hair seen from a distance of over 60 feet, or the size of a tennis ball seen from 8 miles away. The astronomers of the 17th and 18th centuries were attempting to measure an angle even smaller than this, a feat of precision that required instruments of unprecedented stability and accuracy. The slightest tremor in the ground from a passing carriage, the most subtle change in temperature causing the telescope's metal frame to expand or contract by a fraction of a millimeter. The gentle sag of the instrument under its own weight as it tracked a star across the sky. Any of these mundane terrestrial effects could introduce errors far larger than the tiny cosmic signal they were hoping to find. The astronomers of this era were not just observers of the heavens, they were warriors, engaged in a relentless battle against the relentless forces of error and uncertainty. One of the first to enter the fray was the brilliant, cantankerous, and endlessly inventive English scientist Robert Hooke. A contemporary and fierce rival of Isaac Newton, Hooke was a man of boundless curiosity, a polymath who made significant contributions to a dozen different fields. In 1669, he set his sights on the great problem of stellar parallax. With characteristic ingenuity, he designed a special purpose-built instrument, a vertical, or zenith, telescope housed in his rooms at Gresham College in London. The telescope was fixed in a vertical position, pointing straight up through a hole in the roof. His target was the star Gamma Draconis, a bright star in the constellation of the Dragon, which had the convenient property of passing almost directly overhead at London's latitude. By observing a star at the zenith, Hooke hoped to minimize the distorting and blurring effects of the Earth's atmosphere, which are greatest for stars near the horizon. For months, he lay on his back, peering up through his telescope, meticulously recording the star's position as it crossed the meridian. And he claimed success. He announced that he had measured a parallax for Gamma Draconis, a significant and measurable shift. But his results were erratic, and his colleagues, particularly those who were not his friends, were deeply skeptical. It is now widely believed that what Hooke measured was not the true parallax of the star, but some combination of instrumental error and wishful thinking. The ghost had eluded him, and the prize remained unclaimed. Then came the remarkable and serendipitous story of James Bradley, the third astronomer, Royal of England. In the 1720s, Bradley, a meticulous and patient observer, set out on his own quest to conquer parallax. His target was also Gamma Draconis, and his instrument was a state-of-the-art zenith telescope, built with the express purpose of solving this great problem. As he began his observations, he saw it. A shift. The star was not stationary. It was moving, its position changing slightly from one observation to the next, just as parallax theory predicted. The excitement in the astronomical community must have been immense, but as Bradley continued his observations over the course of a full year, a puzzle emerged. The star's apparent motion was not in sync with the Earth's position in its orbit. The maximum shift was not occurring in June and December, as it should if it were due to parallax, but in March and September. The star was dancing, but it was dancing to a different rhythm. A rhythm that was 3 months out of phase with the parallax effect. For years, Bradley was tormented by this anomaly. He was a man of immense intellectual integrity, and he could not publish a result he did not understand. He considered every possibility, from a subtle, undiscovered motion of the Earth's pole to a flaw in his own carefully constructed instrument. The answer, when it finally came to him, was a stroke of pure genius, an insight that would not only solve his puzzle, but would also change our understanding of the very nature of light. He was on a boat on the River Thames, observing the motion of a weather vane on the mast. He noticed that the vane's direction changed depending on the boat's motion relative to the wind. And in that moment, he had his analogy. He realized that what he was seeing in the sky was not due to the Earth's changing position, but to its changing velocity. He had discovered the aberration of starlight. It is an effect we are all familiar with, even if we don't know its name. Imagine you are standing in a downpour on a perfectly still, windless day. The rain is falling straight down. Now imagine you start running. The rain suddenly seems to be coming at you from an angle. You have to tilt your umbrella forward to keep your face dry. The faster you run, the more you have to tilt your umbrella. The same thing happens with light. The Earth is moving at a speed of about 30 kilometers per second through a constant, gentle rain of starlight. Because of this motion, we have to tilt our telescopes slightly in the direction of our movement to catch the light from a star that is directly overhead. As the Earth travels around the Sun, the direction of its motion is constantly changing, and so the direction of this necessary tilt must also change throughout the year. This is what Bradley had observed. It was the first direct observational proof that the Earth is, in fact, moving through space. It was a stunning confirmation of the Copernican model, a discovery as profound, in its own way, as the measurement of parallax itself. But it was not parallax. The ghost had once again slipped through their fingers, but in its place it had left a clue of immense value. The search for parallax had failed, but in its failure, it had revealed something even more fundamental about the universe and our place within it. This became a recurring theme in this great scientific epic. The quest for parallax was a powerful engine of discovery, even as its primary goal remained elusive. In their attempts to measure the tiny parallax angle, astronomers were forced to confront and understand a host of other, more subtle, celestial motions. They discovered the proper motion of stars, the fact that the fixed stars are not fixed at all, but are themselves moving through space, each on its own majestic, solitary journey across the galaxy. They discovered binary stars, pairs of stars locked in a gravitational embrace, a discovery that would become the key to understanding the masses, the sizes, and the life cycles of stars. The 200-year race was a story of glorious failure. Each attempt may have failed to find parallax, but it succeeded in pushing the boundaries of astronomical knowledge, in refining the tools of the trade, and in deepening our understanding of the intricate and complex dance of the heavens. They were mapping the coastline of a new world, even as the mainland remained shrouded in mist. By the early 19th century, the stage was finally set. The technology had, at last, begun to catch up with the ambition. The great lens makers of the era, like the brilliant Joseph von Fraunhofer in Germany, were producing telescopes of a size and optical quality that had never been seen before. The art of precision measurement had been honed to a fine edge by generations of obsessive, detail-oriented astronomers. The problem of parallax was ripe for the solving. It was no longer a question of if, but of who. A new generation of astronomers, armed with new instruments and a deep understanding of the errors and pitfalls that had plagued their predecessors, was ready for the final assault. The race was entering its final dramatic lap, and the man who would ultimately claim the prize was a German astronomer whose name would become synonymous with the measurement of the heavens, Friedrich Wilhelm Bessel. In the grand theatre of science, some names explode like supernovae: Einstein, Hubble, Hawking, bold revolutionaries who tear down old worlds and paint dazzling new ones across the sky. And then there are the quiet architects, the patient masters of detail who build the invisible scaffolding without which no revolution could ever stand. Friedrich Wilhelm Bessel belongs to that second, rarer company. He was not a showman. He was a craftsman of almost monastic devotion, a man who treated measurement like prayer, and while others dreamed in sweeping theories, Bessel lived in the margins of error, chasing down every tremor of a telescope mount, every flicker of atmospheric refraction, every imperfection in a chronometer's tick. To him, the universe did not reveal itself in thunderbolts of genius, but in the slow, stubborn conquest of uncertainty. He pioneered modern data analysis before the term existed, learning to tease truth from noise with a rigor that still feels reverent today. Bessel understood something profound. The greatest secrets are usually hidden not behind complexity, but behind imprecision. Fix the tiny errors, and the cosmos will speak plainly. That is why, when the astronomical community finally accepted that stellar parallax was the only direct path to the distance of the stars, the task fell naturally to him. It was not a job for dreamers or headline chasers, but for a man who could spend years refining instruments, calibrating clocks, and staring at the same handful of stars night after night, hunting for a wobble so small it was measured in fractions of an arcsecond, an angle equivalent to the width of a coin seen from 100 kilometers away. Parallax was never about one brilliant flash of insight. It was about the patient, almost obsessive elimination of 1,000 tiny sources of error, until only the pure geometry of Earth's orbit remained. Bessel was the perfect man for that quiet, brutal work. And when he finally announced in 1838 that 61 Kini lay 11 light-years away, he did not just give us a number. He gave us the first real glimpse beyond the solar system, the first proof that the stars were suns and that the universe was vast beyond all previous imagining. No trumpets, no headlines, just a German astronomer, a modest telescope, and a lifetime of devotion to getting the details exactly right. The parsec begins with him, and every time we quote a distance in parsecs today, we are still standing on the shoulders of that quiet, relentless perfectionist who taught us that the greatest discoveries are often won not in moments of inspiration, but in decades of refusing to accept anything less than the truth. Friedrich Bessel's life reads less like the biography of a great scientist and more like a quiet rebellion against every expectation the world had for him. He was born in 1784 in the small Westphalian town of Minden, the son of a modest civil servant, and at 14 found himself apprenticed to a Bremen trading house. Destined for a safe career counting barrels and balancing ledgers. By day, he tracked cargo across oceans, and by night, he tracked comets across the sky. With no teacher, no university, no patron, he taught himself mathematics, spherical trigonometry, and the fearsome machinery of celestial mechanics from whatever books he could borrow or buy. At 20, still a clerk by day, he recalculated the orbit of Halley's comet with such startling precision that he felt bold enough to send the manuscript to Heinrich Olbers, one of Germany's most respected astronomers. Olbers, astonished by the work of this unknown young man, replied immediately and became his lifelong champion, and within months the merchant's clerk had left commerce forever. The rise that followed was almost unfair in its speed. Observatories courted him, and the King of Prussia, bypassing every academic credential, appointed the 26-year-old autodidact director of the new Königsberg Observatory in 1810, a post normally reserved for grey-haired professors with long lists of titles. Bessel accepted, moved into the observatory, and never really left. For the next 36 years, he turned Königsberg into a temple of precision, building instruments, refining clocks, and training a generation of observers to measure the sky with an accuracy the world had never seen. It was from that quiet Prussian hilltop, armed with a frail 5-inch refractor and an obsession that bordered on the monastic, that he finally conquered the ancient ghost of stellar parallax. The boy who once tallied coffee sacks in a warehouse attic had grown into the man who would hand humanity its first real glimpse beyond the solar system. Bessel's story is the quiet reminder that genius is not always born in lecture halls. Sometimes it is forged in spare bedrooms, lit by candle stubs, driven by a hunger no apprenticeship contract can ever satisfy. The Parsec itself owes its existence to a self-taught clerk who refused to accept the life the world had drawn for him and instead followed the stars. Bessel's weapon in this assault was a magnificent instrument, a masterpiece of 19th century optical and mechanical engineering, the Fraunhofer heliometer. Built by the legendary Joseph von Fraunhofer, the heliometer was a refracting telescope, but with a unique and ingenious design. Its main lens, the objective, was cut in half, and the two semicircular halves could be moved relative to each other along the cut, their separation controlled by a precise micrometer screw. This clever design allowed the observer to create two separate images of the same star field in the eyepiece. By adjusting the separation of the two halves of the lens, the observer could superimpose the image of a target star on the image of a nearby comparison star. The amount of separation required to do this gave a direct and incredibly precise measurement of the angular distance between the two stars. It was a differential measurement, meaning it was largely insensitive to the slow, uniform drift of the telescope or the blurring effects of the atmosphere, which would affect both stars equally. It was a difficult and fiddly instrument to use, requiring immense skill and patience, but in the hands of a master like Bessel, it was a weapon of unparalleled power, the key that could finally unlock the parallax problem. The next, and perhaps most crucial, part of the puzzle was choosing the right star to observe. For centuries, astronomers had focused their efforts on the brightest stars in the sky, like Sirius and Vega, assuming that their brilliance was a sure sign of their proximity. But Bessel, with his characteristic analytical rigor, knew that this was a flawed and potentially misleading assumption. A star could be bright because it is close, or it could be bright because it is an intrinsic powerhouse, a stellar giant shining with thousands of times the light of our sun from a great distance. Bessel decided to ignore brightness and focus on motion. He scoured the star catalogues, which he himself had helped to create and refine, for a star with a large proper motion, a star that was visibly moving across the celestial sphere from year to year. He reasoned that such a star was likely to be a nearby object, a cosmic neighbor whose motion across our line of sight was more apparent simply because it was closer to us, just as a nearby car seems to move faster than a distant airplane. His search led him to a faint, unassuming star in the constellation of Cygnus, the Swan. It was known by its catalogue number, 61 Cygni. It was not a star that would catch your eye on a casual night of stargazing, but for Bessel, it was the most exciting star in the sky. It had the largest proper motion of any star then known, a blistering 5 arcseconds per year. This was a clear signpost, a cosmic X that marked the spot where the treasure was likely buried. Bessel had his target. He had his instrument. Now, all he needed was time and an almost superhuman degree of patience and dedication. In 1837, Bessel began his epic series of observations, a marathon of measurement that would consume him for more than a year. Through the long, cold Prussian nights, whenever the notoriously cloudy weather in Königsberg would permit, he would point his heliometer at 61 Cygni. He was not just measuring the position of 61 Cygni itself, but its position relative to several much fainter stars in the same field of view. These faint stars, he assumed, were much further away and would serve as a fixed, unmoving backdrop, a celestial reference frame against which he could measure the tiny annual dance of 61 Cini. The work was a testament to human endurance and mental fortitude. It was a relentless, repetitive cycle of measurement, calculation, and correction. He had to account for the aberration of starlight, the discovery that had thwarted James Bradley a century earlier. He had to account for the nutation of the Earth's axis, a slight wobble that adds another layer of complexity to a star's apparent motion. He had to correct for the effects of atmospheric refraction, which bends the light of stars as it passes through the air, an effect that changes with temperature and barometric pressure. He had to account for the tiny changes in his instrument's focus and alignment caused by the fluctuating temperature of the observatory dome. He was a man at war with a universe of tiny, confounding errors, a detective on the trail of a signal that was almost completely lost in the noise of measurement. As the months passed, as the Earth swung from one side of its orbit to the other, from the summer solstice to the winter solstice, the numbers began to tell their story. Slowly, painstakingly, a pattern emerged from the sea of data. A tiny cyclical shift in the position of 61 Cygni, a shift that was in perfect sync with the motion of the Earth. It was there. The ghost was in his grasp. In 1838, Bessel was finally ready to announce his result to a waiting and expectant world. He had measured the parallax of 61 Cygni to be 0.314 arcseconds. It was a number of almost comical smallness, a tiny fraction of a single degree of arc. But it was a number that would echo through the halls of science for centuries to come. A number that represented the culmination of a 2,000-year quest. From this tiny angle, Bessel calculated the distance to 61 Cygni to be about 660,000 times the distance from the Earth to the Sun. In modern units, that's about 10.3 light-years. It was a distance that was, at the time, almost beyond human comprehension. It was the definitive, observational confirmation of the vast, empty scale of the universe that philosophers and astronomers had suspected for centuries. The stars were not just distant, they were a different order of distant. The solar system was an island, and the space between the stars was an ocean of unimaginable and perhaps terrifying vastness. Bessel's announcement was a sensation. The 200-year race was over. The ghost of Parallax had finally been captured and measured, and in the very method of its capture, in the elegant, reciprocal relationship between angle and distance, a new way of seeing and measuring the universe was about to be born. Bessel's measurement was a watershed moment, a turning point in the history of human thought. It was the first time a human being had successfully and reliably triangulated the position of a star. The first time we had a firm, undeniable number for the distance to another sun. But the number that made the headlines, the 10.3 light-years, was, in a way, a secondary result. It was a translation, a conversion of the primary, raw result of his observation into a unit that was more familiar, more intuitive to the human mind. The true, unadulterated result of his year of painstaking labor was the angle itself, 0.314 arcseconds, and it was from this angle, this tiny direct measurement of a geometric shift, that a new way of thinking about cosmic distance would emerge. A way of thinking so elegant and so perfectly suited to the problem that it would become the lingua franca of professional astronomy. To understand this, we must return to the vast cosmic triangle that stretches from the Sun to the Earth to a distant star. The short side of this triangle, the side that we can, in a sense, control, is the baseline. Its length is 1 astronomical unit, AU, the average distance between the Earth and the Sun, a distance of about 93 million miles or 150 million kilometers. This is the longest measuring stick we have direct access to, the base of our cosmic surveyor's tripod. The angle at the far corner of this triangle, at the star, is the parallax angle. This is the tiny angle that Bessel, and all who followed him, sought to measure. It is the angle subtended by the Earth-Sun baseline, as seen from the star. What astronomers quickly realized, as they began to grapple with the implications of Bessel's measurement, was that for the very long, skinny, and profoundly isosceles triangles involved in stellar parallax, there is a beautifully simple and powerful relationship between the parallax angle and the distance to the star. Because the parallax angles are so incredibly small, they could use a mathematical shortcut known as the small angle approximation. In trigonometry, for a very small angle, the sine of the angle and the tangent of the angle are very nearly equal to the angle itself, when the angle is measured in radians. This seemingly obscure mathematical fact has a profound consequence. It means that the distance to the star is simply inversely proportional to the parallax angle. In other words, if you double the distance to a star, you halve its parallax angle. If you halve the distance, you double the parallax. This simple reciprocal relationship was a gift from the heavens. It meant that you didn't need to bother with sines, cosines, or any other complex trigonometric functions to calculate the distance. You just needed to measure the parallax angle in arc seconds, and the distance would simply be 1 divided by that number. This led to a brilliantly practical and compelling idea. What if we defined a new unit of distance based on this beautifully simple relationship? What if we defined a unit as the distance at which a star would have a parallax of exactly 1 arc second? This would be the ultimate simplification, a unit of measurement born directly from the method of measurement itself. A star with a parallax of 1 arcsecond would be one of these new units away. A star with a parallax of half an arcsecond would be 2 units away. A star with a parallax of 1/10 of an arcsecond would be 10 units away. The distance in these new units would simply be the reciprocal of the parallax angle. It was a system of perfect streamlined mathematical elegance, and so the parsec was born. It was a unit defined not by the time it takes for light to travel, not by the length of a king's arm, but by the pure, abstract, and timeless beauty of Euclidean geometry. It was the distance at which the Earth-Sun baseline of 1 astronomical unit would subtend an angle of exactly 1 arcsecond. For several decades, this new and practical unit had no official name. It was simply referred to by its definition, a cumbersome but accurate description. But in 1913, the British astronomer Herbert Hall Turner, in a moment of linguistic inspiration, proposed a name that was as elegant and as efficient as the unit itself. In a paper for the Royal Astronomical Society, he noted the need for a concise name for this fundamental unit of stellar distance. He took the first 3 letters of parallax and the first 3 letters of second, and he fused them together to create the word parsec. The name was a perfect piece of scientific poetry, a portmanteau that was concise, memorable, and a definition in itself. A parsec is the distance of a star with a parallax of 1 second. The name was an instant success, and it was quickly adopted by the international astronomical community. The parsec became the standard unit of distance in professional astronomy, the native language of parallax, the natural dialect of anyone working with the geometry of the stars. This is the heart of the parsec paradox, the solution to our central mystery. The unit seems strange and counterintuitive to the outsider precisely because it is so perfectly, so intimately connected to the act of measurement. It is a unit that is custom built for the job, a conceptual tool forged in the crucible of observational practice. It is a beautiful example of how scientists create their own language, their own conceptual tools to better navigate the complexities of the natural world. The parsec is a testament to the idea that in science, the most elegant solution is often the one that is most deeply rooted in the practical reality of observation. It is a unit that is not just a measurement, but a story of a 200-year quest to touch the stars, a story of the triumph of geometry over the vast, silent emptiness of space. And so we arrive at the Great Divide, the schism in the language of the cosmos, a fork in the road that separates the professional astronomer from the amateur enthusiast, the scientific paper from the popular documentary. In one corner, we have the parsec, the practical, efficient, and mathematically elegant unit of the professional astronomer, a unit forged in the heat of observational practice. In the other corner, we have the light year, the poetic, evocative, and publicly beloved unit of the science communicator, a unit that speaks not to our intellect, but to our imagination. It is a classic case of head versus heart, of prose versus poetry. The parsec is the language of the head. It is a unit of pure reason, born from the cold, hard, and beautiful logic of geometry. It is a tool for calculation, for precision, for the rigorous, quantitative work of science that is the necessary foundation for any real understanding of the universe. It is a unit that is stripped of all romance, all metaphor, all unnecessary baggage. It is a tool designed to do a job, and it does that job with ruthless efficiency. The light year is the language of the heart. It is a unit that speaks to our sense of wonder, our deep and abiding fascination with the river of time, our emotional connection to the vast, ancient, and silent universe. It is a tool for storytelling, for inspiration, for bridging the immense conceptual gap between the arcane complexities of astrophysics and the innate curiosity of the human spirit. The human mind, after all, is not a machine for processing abstract data. We are storytellers, and we understand the world through narrative. The light year, with its beautiful and intuitive fusion of space and time, is a narrative device of immense power. It allows us to frame the vastness of space in terms of the familiar passage of time. When we are told that the Andromeda Galaxy is 2.5 million light-years away, we are not just being given a number. We are being told a story. We are being invited to imagine a journey, a pilgrimage of light that began 2.5 million years ago, when our own species was in its infancy, when our distant ancestors were first learning to shape stone, tools on the plains of Africa. The light that we see tonight from Andromeda is a relic of that ancient past, a ghost of a time before human civilization, before language, before art. The parsec, for all its practical brilliance, cannot compete with this. To say that Andromeda is 778 kiloparsecs away is to state a fact. To say that it is 2.5 million light-years away is to evoke a poem. The light year conquered the public imagination in the 20th century because a handful of extraordinary communicators knew that science is only half finished until it lives in people's hearts. Sir Arthur Eddington, with his elegant prose in the 1920s and 30s, and later Carl Sagan, whose voice still echoes across generations in the original Cosmos series, made a deliberate choice. They spoke of light years because the phrase itself is poetry. Every time you say 1,000,000 light years, you are not just quoting a distance, you are summoning time. You are reminding the listener that the photon, now slipping into their eye, left its home before empires rose and fell, before mammals walked the earth, before the sun itself was born. The light year turned cold numbers into a story of cosmic history, a tale of looking outward and simultaneously falling backward through the ages. It was the perfect bridge between the laboratory and the living room, the unit that made the universe feel alive. Yet step inside any real observatory, open any serious research paper, and the light year almost vanishes. There, on the computer screens and in the notebooks of the astronomers who actually measure the sky, you will find distances quoted in parsecs: 3.26 light-years, 12.9 parsecs, 850 kiloparsecs. The unit looks archaic, almost comically obscure, and most working astronomers will admit they rarely convert it back to light years except when talking to the public. This is no accident, no stubborn tradition. The parsec is not just a rival unit, it is the foundation stone of everything we know about the size of the universe. It is the indispensable first step on the cosmic distance ladder, the chain of overlapping techniques that lets us climb from the nearest stars to the very edge of the observable cosmos. Without the parsec, the ladder has no base. Without the parsec, every distance beyond a few hundred light-years collapses into guesswork. The light-year inspires, the parsec delivers. And the reason it delivers is a story of pure geometry, exquisite precision, and one of the most beautiful coincidences in all of astronomy. The cosmic distance ladder is one of the most elegant constructions in all of science. Not a machine, not a telescope, but a chain of pure reasoning that lets us reach from the nearest star to the very horizon of the observable universe. Each rung is a different technique: parallax, Cepheid variables, type Ia supernovae, redshift, and more, and each depends on the one below it for its calibration. Pull out a single rung and everything above collapses. Errors cascade upward like cracks in a dam until the farthest distances become little more than wishful thinking. The entire tower stands or falls on the strength of its foundation. And that foundation is stellar parallax. Parallax is the only truly direct, assumption-free way we have to measure distance in the universe. It is simple geometry. Watch a nearby star drift back and forth against the fixed background of distant stars as Earth orbits the Sun. The size of that tiny wobble, measured in arcseconds, tells you the distance in parsecs by a definition so pure it feels like magic. 1 parsec is the distance at which one astronomical unit subtends 1 arcsecond of angle. No assumptions about brightness, size, or physics required. Just triangles, the diameter of Earth's orbit, and the unchanging clockwork of the sky. Because the parsec is born directly from this geometric method, It is the native currency of the distance ladder's bottom rung. When the European Space Agency's Gaia mission delivers parallax distances to 2 billion stars with micro arcsecond precision, those distances come out in parsecs first, naturally, effortlessly. That exquisite catalogue becomes the calibration set for everything else. The true brightness of Cepheid variables, the peak luminosity of type Ia supernovae, the standardization of entire galaxy populations. The parsec is not an affectation, it is the anchor. Every number we quote for the size of the universe, the distance to Andromeda, the scale of the cosmic web, the age of the Big Bang itself, ultimately traces its reliability back to those tiny parallax wiggles of nearby stars. The light year may sing to the soul, but the parsec keeps the ladder from falling. It is the quiet, indispensable hero of cosmic measurement, the reason we can stand on Earth and claim, with straight faces, to know how far away the edge of the observable universe really is. The next rung on the ladder, the one that allows us to take our first great leap out of our immediate solar neighborhood and into the wider galaxy, belongs to a special and wonderful class of pulsating stars called Cepheid variables. These stars are cosmic lighthouses. They are not stable, steady points of light. They are giant, unstable stars that rhythmically expand and contract, growing brighter and dimmer with a period that is as regular as a ticking clock. In the early 20th century, a brilliant and tragically under-recognized astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory, made a discovery of monumental importance. Leavitt was one of the Harvard computers, a group of women hired to perform the painstaking and often tedious work of examining photographic plates and cataloging the properties of stars. While studying thousands of variable stars in the Magellanic Clouds, 2 small satellite galaxies of our own Milky Way, she noticed a remarkable pattern. She found a direct, unambiguous relationship between the period of a Cepheid's pulsation and its apparent brightness. The longer the star took to complete one cycle of brightening and dimming, the brighter it appeared. Since all the stars in the small Magellanic Cloud are at roughly the same distance from us, their apparent brightness is a direct indicator of their true intrinsic brightness, their absolute magnitude. Leavitt had discovered a period luminosity relationship. This was a discovery that would change the course of astronomy. It meant that Cepheids could be used as standard candles. If you could measure the pulsation period of a Cepheid, you could use Leavitt's relationship to determine its true intrinsic brightness. And if you know its true brightness, you can compare that to its apparent brightness in the sky, and from that, using the simple inverse square law of light, you can calculate its distance. But there was a crucial missing piece. Leavitt's relationship was a relative one. She knew that longer period Cepheids were brighter, but she didn't know exactly how bright. To make the Cepheids a true tool for measuring absolute distances, the period luminosity relationship had to be calibrated. Astronomers needed to find a Cepheid that was close enough to have its distance measured directly by parallax. This was a major challenge, as Cepheids are relatively rare and the nearest ones are still quite far away. But eventually, with the advent of more powerful telescopes, they succeeded. By measuring the parallax of a few nearby Cepheids in our own galaxy, they were able to determine their true distances, and thus their true absolute brightness. This allowed them to calibrate the entire scale, to put a number on Leavitt's relationship. Now, whenever they saw a Cepheid variable in any galaxy, no matter how distant, they could measure its period, determine its true brightness, and calculate its distance. The cosmic distance ladder had a second, powerful rung. With the Cepheid variables, astronomers could measure distances to nearby galaxies, out to about 100 million light-years. It was this technique that allowed Edwin Hubble in the 1920s to prove that the spiral nebulae, like Andromeda, were not clouds of gas within our own Milky Way, but vast distant island universes in their own right. A discovery that expanded the known universe by a factor of millions. But beyond about 100 million light-years, even the brilliant Cepheids become too faint to be seen with our telescopes. When the white dwarf's mass reaches a critical, precise limit, known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, it can no longer support itself against its own gravity. It collapses and ignites in a runaway thermonuclear explosion that tears the star apart. Because all Type Ia supernovae are thought to explode at this same precise mass limit, they are all believed to have very nearly the same peak luminosity. They are like cosmic lighthouses, all of the same, brilliant wattage that can be seen across billions of light-years. By finding these explosions in distant galaxies and comparing their apparent brightness to their known intrinsic brightness, astronomers could measure distances to the far reaches of the universe. And how do we know the true intrinsic brightness of a Type Ia supernova? We know it because we have been lucky enough to observe them in nearby galaxies whose distances were first determined using Cepheid variables. And the distances to those galaxies were measured because we could calibrate the Cepheid scale using parallax. It all comes back to parallax. It all comes back to that first, fundamental, geometric measurement of a tiny angle in the sky. It all comes back to the parsec. It is the thread that ties the entire cosmic distance ladder together, the anchor that grounds our knowledge of the universe in the solid bedrock of geometry. Without it, our understanding of the size of the universe, the age of the universe, and the astonishing discovery that the expansion of the universe is accelerating, a discovery made using Type Ia supernovae, would all be built on sand. For most of the 20th century, stellar parallax remained a heroic but agonizingly limited art. Even with the world's greatest telescopes, the Earth's atmosphere was a cruel jailer, and every breath of air, every ripple of heat and turbulence smeared the positions of stars across the sky like wet ink. From the ground, reliable parallaxes were possible for only a few thousand of the very nearest stars, and even those carried uncertainties that made astronomers wince. The cosmic yardstick was accurate in principle, but painfully short in practice. To break free, we had to leave the air behind. In 1989, the European Space Agency launched Hipparcos, a modest satellite named after the ancient Greek stargazer who first tried to map the heavens 2 millennia earlier. Aloft above the blurring veil of our planet's atmosphere, Hipparcos spent 4 years staring at the sky with unblinking clarity, measuring the positions, brightnesses, and, most crucially, the parallaxes of more than 100,000 stars with a precision roughly 10 times better than anything achieved from the ground. For the first time, we had a true three-dimensional skeleton of our stellar neighborhood, a map stretching hundreds of light years in every direction with real, trustworthy distances. Hipparcos was a triumph, a proof of concept that sent shockwaves through astronomy. It refined the zero point of the period-luminosity relation, sharpened our calibration of Cepheids, and quietly rewrote thousands of textbook numbers. Yet, it was only an appetizer, for its catalogue, revolutionary as it was, still reached only a fraction of the Milky Way's volume. The stage was set for something far grander, a mission that would not merely improve the map, but redraw the entire galaxy in breathtaking detail. The atmosphere had been conquered, the age of space-based parallax had truly begun, and with it, the promise of distances so precise they would anchor the cosmic distance ladder for generations to come. In 2013, the European Space Agency ignited a revolution with one spacecraft, Gaia. This is not merely a telescope, it is the ultimate cosmic surveyor, a machine built for one purpose: to map our galaxy in 3 dimensions with a brutality of precision that borders on the absurd. Over its lifetime, Gaia has measured the positions, distances, and motions of more than 2 billion stars, roughly 1% of the entire Milky Way. 2 billion. Count one number per second, without sleep or pause, and you would need 63 years just to reach Gaia's tally. At its heart, Gaia is the greatest parallax engine humanity has ever built, doing what Friedrich Bessel did for 61 Cygni in 1838, but on a scale that would have seemed insane to every astronomer who ever lived before it. Where Bessel wrestled with tenths of an arcsecond, Gaia works in micro-arcseconds, or millionths of an arcsecond. The angle a euro coin on the moon would subtend from Earth, the width of a human hair seen from London to New York. It is precision so fine that Gaia can detect the gentle wobble of a star caused by an Earth-sized planet orbiting at one astronomical unit, or measure the drift of stars across the sky at walking pace from 1,000 light years away. Freed from the atmosphere's restless shimmer, operating from its quiet perch at the L2 million miles beyond Earth, Gaia stares at the same billion stars again and again, year after year, building up a 3-dimensional movie of the galaxy in motion. Every parallax it delivers is spoken natively in parsecs, with uncertainties so tiny that for the first time in history, the bottom rung of the cosmic distance ladder is forged from billions of measurements instead of a desperate handful. This is not incremental progress. This is the moment astronomy grew up. Gaia has turned the Milky Way from a 2-dimensional photograph into a living, breathing, 4-dimensional sculpture. And because every distance it spits out is a parallax distance, pure geometry, no astrophysical assumptions, it has recalibrated the entire cosmic distance ladder with ruthless authority. Cepheids, RR Lyrae stars, type Ia supernovae, every standard candle we use to climb farther out now rests on a foundation of 2 billion parallax anchors. The parsec is no longer just convenient. Thanks to Gaia, it is triumphant. To achieve this, Gaia is a marvel of engineering, a spacecraft designed with a single-minded focus on stability and precision. It is a spinning spacecraft, constantly scanning the sky with its 2 telescopes, which are pointed at a fixed angle relative to each other. As the spacecraft rotates, the 2 telescopes sweep out great circles on the sky, and the light from the stars is focused onto a focal plane of nearly 1 billion pixels, the largest digital camera ever flown in space. Gaia has no moving parts apart from its thrusters and a large deployable sun shield that keeps the telescope in a deep, stable cold. The entire spacecraft is the instrument. It is located at a special, gravitationally stable point in space, the L2 Lagrange point, about 1,000,000 miles from Earth, where the gravitational pull of the Earth and the Sun are balanced. This provides an incredibly stable platform for observation, far from the distorting effects of the Earth's atmosphere and the thermal instability of a low Earth orbit. Over the course of its multi-year mission, Gaia will observe each of its billion target stars an average of 70 times. Each time, it records the star's position, its brightness, and its color with exquisite precision. By combining these tens of billions of individual measurements, Gaia's powerful data processing system, a global effort involving hundreds of scientists and engineers, can disentangle the various motions of the stars. It can separate the tiny cyclical wobble of parallax from the slow, linear drift of proper motion, and from the apparent motion caused by the spacecraft's own movement. The result is a dataset of staggering richness and complexity. It is a 5-dimensional map of the Milky Way. For each star, Gaia gives us its 2-dimensional position on the sky, right ascension and declination, its parallax, which gives us its distance, the 3rd dimension, and its 2-dimensional proper motion across the sky. And for many of the brighter stars, it can also measure their radial velocity, their motion towards or away from us, using an onboard spectrometer, giving us the full 6-dimensional picture of their journey through the galaxy. The Gaia data releases have been a series of seismic events in the astronomical community, each one unleashing a torrent of new discoveries, a flood of new papers, a fundamental rewriting of our understanding of the Milky Way. With Gaia, we are no longer looking at a flat, 2-dimensional photograph of our galaxy, a beautiful but static projection of its true structure. We are seeing it as it truly is, a dynamic, living, breathing, 3-dimensional structure, a swirling city of stars with a complex history and a vibrant present. We can see the majestic sweep of the spiral arms, the great river of stars that forms the central bar, the subtle warp and flare of the galactic disk, which tells us about the gravitational influence of our satellite galaxies. We can see the history of our galaxy written in the motions of its stars. We can see the ghostly trails of smaller galaxies that the Milky Way has cannibalized and devoured over billions of years, their stars still moving together in great stellar streams, like the lingering ghosts of galaxies past. We can trace the birthplaces of stars, the open clusters and associations where they formed, and watch as they drift apart to populate the galaxy. A process of galactic dispersal that was previously only theoretical. We can test our theories of stellar evolution with a precision that was previously unimaginable. By placing tens of thousands of stars on a Hertzsprung-Russell diagram with precisely known distances and luminosities. We can weigh the galaxy, and in doing so, map the distribution of the mysterious invisible dark matter that holds it all together by observing its gravitational influence on the motions of the stars. The Gaia Revolution is a story that is still unfolding. The mission is ongoing, and the full dataset has yet to be released, but it has already changed the face of astronomy. It has transformed our picture of the Milky Way from a static 2-dimensional photograph into a vibrant, dynamic, 3-dimensional movie. And it all rests on that one fundamental measurement, parallax. It all comes back to that tiny geometric shift, the same shift that Bessel first measured in a single faint stare with a brass and glass instrument in a cold, damp observatory nearly 200 years ago. Gaia is the ultimate expression of the power of the parsec. It is a mission that has taken a 19th century concept and scaled it up to a level that is truly cosmic. It is a powerful and humbling reminder that even in the age of space telescopes and supercomputers, the fundamental principles of astronomy, the elegant geometry of the parsec, are as relevant and as powerful as ever. And so, our journey through the strange and wonderful world of the parsec comes to an end. We have travelled across millennia, from the sun-drenched shores of ancient Greece to a lonely, silent point in space 1,000,000 miles from Earth. We began with a paradox, a simple question. Why do astronomers use a strange, counterintuitive unit of distance called the parsec? And the answer, we have discovered, is as profound and as beautiful as the universe itself. The parsec is not just a unit of measurement, it is a story. It is the story of our relentless, multi-generational quest to find our place in the cosmos, to measure the immeasurable, to know the unknowable. It is a story that begins with the comforting, human-scaled universe of the ancients, a celestial sphere that was both a ceiling and a home. It is a story of the intellectual courage of Copernicus and Galileo, who dared to shatter that sphere and cast humanity adrift in a universe of terrifying, unimaginable scale. It is the story of a 200-year race, a marathon of human ingenuity and patience to measure a tiny, almost imperceptible shift in the positions of a star, a ghost that haunted the observatories of Europe. It is the story of Friedrich Bessel, a man whose meticulous obsession with precision finally allowed him to touch a star with the pure power of geometry, and in doing so, to give us our first true sense of the immense, silent void that separates us from our cosmic neighbours. The parsec was born from that moment of triumph. It is a unit that is not based on the speed of light or on any arbitrary human convention, but on the very act of measurement itself. It is a unit of pure geometry, a testament to the power of mathematics to reveal the hidden structure of reality. It is a unit that seems backwards, that defines a distance by an angle, but in that backwards logic lies its brilliance. It is the key that unlocks the cosmic distance ladder, the foundation upon which our entire understanding of the universe is built. From the parallax of nearby stars, we calibrate the Cepheid variables that allow us to measure the distances to nearby galaxies. From those galaxies, we calibrate the type Ia supernovae that allow us to probe the deepest reaches of space and time, and to discover the astonishing fact that the expansion of our universe is accelerating. It is all connected. It is all built on that first, fundamental rung. And today, with the Gaia spacecraft, we are living through a revolution in our understanding of the parsec. A revolution that is transforming our map of the heavens from a flat, static picture into a dynamic, three-dimensional epic. So, the next time you find yourself under a dark, clear sky, the next time you feel that familiar, primal sense of awe and wonder, take a moment to remember the parsec. Remember the story of the human minds that dared to measure the immeasurable. Remember that the universe is not just a collection of cold, hard facts and figures, but a grand, unfolding narrative. And we, with our strange and beautiful units of measurement, are its storytellers. The universe is full of these beautiful paradoxes, these strange truths waiting to be discovered. What cosmic mystery should we explore next? Let us know in the comments below. Until next time, keep looking up